let me first say a little bit about how in practice you would actually try to put a smooth structure on a category. And then see what you have to understand, some kind of a rather local construction and the compatibility of different local constructions you can do. And then the question is, how can we do this local construction that would lead to this black box theory, which is sort of a very local theory. So I would have a category, and the category would have the following properties. First of all, so every morphism is invertible, and between two objects there are only finitely many morphisms. And the third thing, it would come with a topology on the orbit space. That means if I, and this is a set. So if I identify isomorphic objects, I get a set, and it has a topology. It's a metrizable topology. So what you would like to do is, in concrete cases, rather construct an EP groupoid, so which is a set, is a smaller category, but now it has smooth structures together with an equivalence of categories. And of course, you would in general construct several of this, but there should be some compatibility, which I'm not going to tell you. But what does it mean in practice? What would you do? So here's my category, and the category has possibly the fact it could be probably very large. Now, that the category is very large comes from the fact that there are many things which are isomorphic, but the isomorphism class is still a set. So a smooth structure should be viewed as constructing somewhat local slices, where in this direction you view the isomorphism classes as an orbit of a group action. Yeah? So you could think of a group acting on a space, and the equivalent thing here would be the orbit would be the isomorphism classes of a given object. And you want to construct, in some sense, local slices. Takes the disjoint union of the local slices, which will be that space. You have the inclusions. Then on these slices, you would like to define a smooth structure. And then you want to show if two slices are equivalent by morphism the category, then if you move that thing here smoothly, the arrow here moves smoothly as well. So X is a disjoint union of slices. Enough slices that every object, that you hit every isomorphism class. So, huh? Yeah, union of truncate. So the point would be to construct now the local slices. That would be one of the things. You would have to construct a local slice. So what would that mean in practice? Well, you would have to come up with a recipe, a general rule. If you take an object in the category, do this, and this, and this, and you follow that rule. It might not lead always to the same result, but at least if different results are obtained, they're in some sense nicely compatible. So one would come out, one would have to give a method how to construct for a given object a local slice. So like homology is a recipe, if I give you a topological space, construct the following. That's so on that level. So now the first thing is, so I'm giving an object in C. Then, since between two objects there are only finitely many morphisms, it has the stabilizer, so it has an automorphism group, which is finite.
Actually, quick question. So when you write embedding, you mean that it's injected
Equivalents are right.
on the level of objects?
No,
It need not be
No.
injective on the level.
no. An equivalence is not injective on the level of objects.
So then if you
An equivalence only has a property that the number of the objects, the morphism between two given things go bijectively to the things in the image.
so are you going to introduce new morphisms into X when the arrow into C is when the object
No,
in
why?
C is
Not necessarily. Why? No, a notion of an equivalence in category theory is okay. So that's precisely what we require. That's it.
But then this is not going to be injective on the
Why does it have to be injective? Category theorists have. So why should it be injective?
So once you quotient out by morphisms,
I did when I quotient out on the of course on the level after quotienting out it is actually bijection. Yeah.
Also, let me ask this again. So now you have two in the application, right? You have two different local slices, right? In the object space of X, right? And somehow they happen to intersect at a point, right? There's one map that sits in two different local slices, so now it gets mapped into C
Yes.
twice,
Mhm.
right?
And
So there's 2 points and 2 objects in X that get mapped to the same object in C.
yes.
Will you put a morphism between them in X?
No. The only requirement is that if I have two objects here, the morphisms between them go bijectively to the morphisms which exist here between these two things.
Then you're not going to get a bijection between the two.
Of course you get.
organizations.
Of course you get.
No. Because at X you're going to, I mean, the two different points
So,
in
I
the
mean,
local slice now are actually different points in X modulo morphism.
Of course you have here between the since you obviously have a morphism here, you actually have to have a morphism here as well.
So the answer to my question is yes, you do put a morphism between the different points of X.
I put them so that this is ultimately an equivalence, yes.
So you do want it to be injective on the level of, I mean,
It's not injective on the level of objects. It is definitely not injective on the level.
you do put in a new morphism.
What is new? I'm constructing this. There's nothing old and new here.
No, I think you also require that on the equivalence proposition objects, which is bijection.
No, that is automatic if you construct something which is if you have if you have two objects and look at the morphisms between two objects and you look at the morphisms between the imaging objects, that the functor is actually bijection between them, and every object can be here reached by taking a suitable point object here, going here, and then by an isomorphism to that other thing. If you have this, then automatically, if you pass to the isomorphism classes, you get a bijection.
Yeah, you left out the second condition.
I said it's an equivalence, which means the letter.
No, but when you explain what equivalence that when you have two objects, well, the last thing you said two
Okay.
things.
So
Last thing when you said two things, you left out.
okay, so that we don't have any difficulties in future. And let's call this F. F would be here, and given C, there exists X, and a morphism to C. Given object of C, there exists X, and there exists phi. So now, if
Don't you also require that if you have two different things in X, they go to the same thing in C?
no, because of the so claim is under these conditions, if you pass to isomorphism classes, you get a bijection. But it does not require you that actually on the level of objects you are injective. So for example, well, clearly by this property you reach every element here in the in the quotient. So if you pass, so if you have these conditions here. So claim first you have a well-defined map here. If we take equivalent things here, they obviously take a representative, you go to a class here. So you have an induced map here. It's surjective because every element can be reached in this way. So assume two things go to the same class, by that property, then they're already isomorphic. So it's a bijection.
Oh, so the answer to my question is there's an identity morphism that proves that on C, right? If you have two different objects in X that go to the same in C, and you have the identity morphism of C, and you say that
Well, that would come from the idea. Okay, so
it has to come from a morphism in X.
yeah, so the identity morphism would. Well, there would be actually. Okay, so there might be different scenarios. So the question would be if f of x is equals f of y, yeah? Okay, so these are objects, they're isomorphic. So there could be the identity morphism, but the identity morphism, yeah, well, would come from some other morphism between x and y. Yeah, okay. So you only need this bijection on the level of morphisms, yeah, if you fix two objects to the image object and the other that you can reach everything. So now, so the recipe would now have to, of course, I cannot construct from an arbitrary topological space a manifold structure, so I can only say what the requirements would be, and in concrete cases, you are usually able, because the problems are geometrical, to come up with something along these lines. So if sigma is an object in C and G is the automorphism group of sigma, then what we want to construct, so one would like to construct M polyfold O sigma with a G action. So this can be viewed as a category where the objects are this and the morphisms are things of this kind, GX, GX. Yeah? So a space with a group action is turned into a category like this. And then you want to construct a psi sigma into C. You want perhaps to have a specific element here which goes to your sigma. And this should be full and faithful, which means, so this should be a functor. This would mean any morphism between two imaging things comes from G. And every morphism between two image objects comes from a morphism here. Yes? And morphisms here go to different morphisms here. Yeah? So that is first requirement. Because otherwise, when you take disjoint union of those, you would not be able to get something which is which would have this property here. And then,
So could you say again what you said about morphisms?
so what you can look at is if you have 2 points take the images of 2 different points, and you have a morphism in the category here. It should come from a G. So then there should be a unique G so that Q prime is equals this.
So in that statement, you fix Q and Q prime.
Given Q and Q prime, and I take any morphism between these images, it comes from a unique G.
So then
No,
Same V for different Qs.
yeah, but the morphism, no. If I have different Qs, but it could happen that for that for different Qs, I have the same object in the category. That could happen. So it's not. It need not to be injective on the objects. It just has precisely this property which I just described. And here's of course a test. If you do a good thing, is that if you take, or maybe I should quotient in the front and whatever. If I take the quotient here, then I get an induced map into this thing. This should be a homomorphism onto an open set. Yeah, so that is a test if you're doing at least locally the right thing compatible with the topology which you have on that space. Sigma is the object I originally picked. So the general thing that you, in order to construct smooth structures in a category, you have to come up with some kind of a functorial description which tells you, if you pick an object in your category, you do this and this and this and this, and which is a construction of a map is a construction of a polyfold with a distinguished point and a map into your category which maps the distinguished point to the object which was given to you. This map here, this is a functor. It should be full and faithful, which is the property which I described. And if you pass to quotient spaces, you get a homomorphism onto an open subset. So this is some kind of the minimal requirement for the local construction. Now, so at this point, we have a recipe for a local construction around every point for given any object. Yeah?
For full and faithful, you also want to suppose that phi is psi sigma of G.
Yes, this is what I said here. So psi sigma of Q, G, Q prime is phi. Yeah, so that is the first test of a good local construction in this business. So this is number one. So the number two now, compatibility. So now, given sigma and sigma prime, consider this object here. So these are already two things which you can construct. Consider now this here. This consists of all Q, phi, Q prime, such that phi is a morphism from psi sigma Q to psi sigma prime of Q prime. The prescription, so the recipe, so there is a construction of an M polyfold structure for that set, so that the following holds. So the first part is you have something like good local parameterizations, yeah. So at least they parameterize something here, which is tested in this way. The next thing is if I take two local parameterizations, I consider this thing here, which is in some sense should describe the relationship between two parameterizations. It's like the transition map for two charts. That is this object here. And you want the recipe or the method should equip this with an M polyfold structure with the following properties. One, so this obviously has two maps, a source map onto O sigma and a source map on O sigma, and a target map onto sigma prime. And they should be local SC diffeomorphisms. Yeah, so the projection onto the Q factor or the Q prime factor should be SC diffeomorphisms. So that's what the construction should give you. So maybe I should put some bullets here. So that's okay. Well, it's like up to the ambiguity. So suppose we would be in a case where we have at most one morphism, then that would be the manifold case. That is equivalent to saying that the transition map of the charts is smooth in both directions. Yeah, because the transition map of the chart is just going backwards with that guy and then down with this guy. So it's equivalent. It's like the transition. If this would be manifolds, like the transition map of two different charts is smooth. That's precisely what that means. So now, and then the next thing is we are in a category, so we have all the standard maps. We want them to be smooth. So the map from O sigma into M psi sigma, these were the things defined on O, which associates to X1X, this morphism. The one morphism, so what is the one morphism is Q, Q, it, Q. So this would be Q at psi sigma of Q. 1 psi sigma of Q. Q is SC smooth. That is what you want to have. And then the map prime to where I interchange the order of those guys. So here we have Q phi Q prime, and you map it to Q prime phi inverse Q. The inversion map should be SC smooth, which then implies actually an SC diffeomorphism. Yeah? And then the third thing is this 1 prime, then here you take, let me say 1. Yeah, okay, so let me put here target, source, M psi sigma prime, psi sigma double prime. So let me observe here, since S and T are local diffeomorphisms, then I can build this firebot product, and this it has a natural polyfold structure. Yeah, so where the source equals the target. So this has a natural structure, and then you have the multiplication map into M of psi sigma double prime. This should be SC smooth as well. Yeah, the composition, obvious composition. Yeah.
Are you saying that this fiber products of polyfolds are of M polyfolds or M polyfolds?
No, if you have two M polyfolds and you have a local diffeomorphism into a third one, then you can build the fiber product. It's naturally an M polyfold. But the projection should be local diffeomorphisms. Actually, it suffices that one of them is local diffeomorphism. So this should be the properties. And now you can define an EP groupoid. Namely, you just take all those guys, and you can find a collection of objects, sigma I, so that if you look at sigma I, takes the image of this. This is a covering, open covering of C. So now, since this is a metrizable space, you find a smaller covering, which is locally finite covering. So you take a locally finite subcover, and then take pre-images of these things, which means you trim the O's. So you can take subsets of a corresponding choice of O's, so that the images are, so that means you, by going through this thing, that given any covering, you can find a refinement which is locally finite. Then for such a refinement, then you go back, find a thing, and take the pre-image, which gives you a subset of that corresponding O here. So what you can construct out of this are new parameterizations which have smaller domains, so that if you look at the images, it's a locally finite covering. So the end result of this is there's a suit, so you take the disjoint union of certain of those guys, and if you look at the images of those, it's a locally finite covering of your C. The reason that I need this is for the properness condition. That gives a properness condition. So we take this, so we find O sigma I, so that so let's say twiddle, so I have to modify them. These are subsets of previously constructed sets. So that psi sigma I, O sigma I, twiddle is a locally finite covering of C. So now your X is this disjoint union of this thing, so that is an M polyfold. And then I can look at the M spaces if I take two different choices here. So the X would be the disjoint union of this restricted things. And then by this property that this was a locally finite covering and the other property is verified, this is actually an EP groupoid. EP groupoid. Since the images are still covering, it's obviously, you can reach any element. So now you have a natural inclusion into the C here. Not an inclusion, a natural map, which is an equivalence by construction. So that is now what I call a smooth structure on C. But I made certain choices of my objects. So now, yeah, properness basically means that if you have a groupoid like this, that any point in the orbit space, if you go to the category C and take
Sorry, is this the standard definition in groupoids?
what?
Source times target is a proper map.
No. If you wouldn't running out all the time, no, it's my properness definition because the other doesn't make sense in infinite dimension.
Okay, can you say that abstractly?
Yes, I can say that. It means that every point in the orbit space of C has a neighborhood which is only hit by, in X, there are only finitely many, is a finite cover, basically. C is a big category. But the orbit space has a topology. So is a neighborhood which is only covered by finitely many of those six. There are only finitely many eyes whose image would actually contain, which actually hit that neighborhood.
So the map from objects of X to the topological realization of C is finite to 1.
From the, yes, so yes. If you go to this topological space, only a finite number of these O's would actually, if you pass this equivalence class, would hit this neighborhood of the point.
So not just.
I mean, this is a stronger condition what actually properness means, but it implies properness. How I defined this.
It implies the standard properness?
No, the standard properness doesn't make sense in infinite dimensions.
Okay, right.
My definition of properness is every point in the object in my EP groupoid has a closed neighborhood, so that this map from there into X is proper. Every object has a neighborhood if I take the pre-image of its closure by S.
So the X is in
Object.
objects of X.
In my EP groupoid.
Okay.
And it has a neighborhood. If I take the closure of this neighborhood, it takes a pre-image under S. And S inverse. Take S inverse of S, which is a pre-image under S. Yeah? Then if I view T, the target map from this onto X, this is proper. The pre-image of a compact set is compact.
This map is proper. Okay.
Yes, that is properness in this context. Actually, if you go to finite dimensions, since you have locally and put it together, I think, as far as I remember, it implies the usual properness in finite dimensions in the sense that they require that that pair S, T is proper. In finite dimensions, for proper Lie groupoids, they require that this map ST is proper. But in infinite dimensions, that doesn't make sense. So, in general. So that's my properness. And if you have this locally finite covering thing, that is actually implied.
You've written on the second line in that part there, it's a disjoint union of IM.
Yes, so it takes a disjoint union of this O. Huh, what? A bold N. Oh, that's a bold N. So this would be your morphisms, and then these target map and source maps are these usual projections onto the factors as before. And then this properties here will tell you it's an EP groupoid. And then you see if you make two such constructions by taking different choices for your open covering. One gives you X, one gives you X prime. Then if you take the union of these two constructions, it's also locally finite covering, you have natural inclusions into this. You have, say, natural maps into these things, which are equivalences. And then this means you can actually define the fiber product, and there's some abstract theory what you should consider equivalent EP groupoid structures on this thing. So I'm not going further into this. But it turns out if you have this construction, there is, in an abstract sense, a well-defined smooth structure on this category. So, okay. So now if you look at this, what I just described, so this is a scheme you have to follow. So usually the category comes from something really geometric. You have to think, what does it mean? I have an object. What is a neighboring object? When I talk about neighboring object, you should think of a slice of neighboring objects. Now, so a neighborhood in the category is not something like this. It's just a thin set-like slice, and in this direction, it's not even a set. That is what you should think of a neighborhood of a small slice. And in general, like, look at the stable maps. You can almost imagine what should be a neighboring thing. You want basically, so you want to remove the nodes, but there's a natural way how to glue two things together at a node, so that gives you a natural choice of a family, of a finite family of surfaces. Then you have to think a little bit how you glue this, how do you find the maps. So you use some kind of this gluing, which you saw today for the Moch theory case. There's a version of this. Then you want to modify the maps. If a way where you don't glue, you have the same surface. You want to be in the Sobolev class sufficiently close. So there's some natural things you will say, what should be a closed object that will be defining the slice. So once you do it for one case, you develop what you look for. So if you have deal with a geometric category, it's usually rather easy to say what you would consider as such a local slice. So now, so this black box business is now concerned with actually constructing local slices, because even since it seems to be really tiny and small, usually it's already a heavy-duty construction itself, the local slice, because you have to think about, say, in Gromov-Witten, how to remove the nodes, what is the neighboring map on, then you remove the nodes, and so on. That's already heavy-duty. And since these considerations occur in every paper ever written, you want to do it once and for all and give it some kind of a guaranteed approval that that actually has been done correctly and can be reused by some general nonsense. Yeah? So once people agree that that has been done correctly in the right way, it can be reused without being actually repeated as part of a construction where you construct 500 different things at the same time, which you have to control. You just want to do it once, and then you know it plays together with other things. And you want to give a recipe or some general set of rules which says, if you make a good construction, it has to adhere to the following rules, and then some general nonsense would tell you it would interplay nicely with the other things you already constructed. So it's a question of keeping the local complexity under control. Okay, so that is what the purpose of the next thing is. So are there any questions so far? Is that is it all clear already on a painful level? Yeah?
Well, you don't need any topology on your category for C.
Yes, you would not, yes, it's true. You could actually define the EP group or then pass to the quotient, get a bijection, said, put that topology on it. Yes, you could say,
So
you,
in this top box there, this curly C, you don't assume a topology
no,
for C?
actually, yes. So yes, okay. So I actually would prefer that the category would come with a topology on this thing. That already tells you, when you do the topology, you do at least some rough estimation what you would consider things close and so on. But in principle, of course, you don't have to. You could just construct an equivalence. You construct an X, which is an equivalence to this category. Then you pass to the quotient. This is a bijection. Now, this space X, if it's proper, if you have a proper EP group point and pass to the quotient space, this has a natural Hausdorff topology. Yeah. And then you would at least get a Hausdorff topology there. And of course, if the group point is not, so if, for example, if you know it's second countable and so on, then it's actually metrizable. I mean, it's metrizable always. It's within metrizable always. Yeah, so the quotient is, I think, is always metrizable. And then, since it's bijective to the orbit space of C, then the orbit space of C would inherit the topology by just pushing it forward. But I think, from a practical point of view, I mean, you don't do the heavy-duty lifting at the first. You first meditate over this category and think what could be sort of close and so on, and identify some kind of a topology. Because if you succeed with the whole program, there will be a topology on the quotient space. But let's forget about smooth structures, everything. Since we know at the end there will be a topology, why not trying to find it at the beginning, what looks like a reasonable topology? Because then it already helps you when you do the local construction. This is some test if you're doing the right thing.
So let me better ask that again.
Mhm.
A topological structure on your big category C would not help you.
It can exist as a class, not a set.
Okay, so there's no meaning of that.
It does, in general, no meaning of this.
But in your present definition of smooth structure, you have not made any requirements of how the metrizable topology on this quotient space is related to X. But are you saying that norm F should be homomorphic?
No, so you could start with a category C, make a construction of group points, push this forward, the topology, onto the quotient, and then the notion of equivalence of group points would actually tell you if you take any other group point, it would give you the same topology.
So if you start with a metrizable topology, then you want norm F to be a homomorphic.
Then F you want to be a homomorphism, yes. But which will be automatic because locally, the local construction already have a local homomorphisms. You put this all thing together, since it's a bijection, it's invertible, and being a homomorphism is a local thing. Okay. So now so how would a local construction look like? So I would, for example, get a noded sphere together with a map U into my symplectic space. So that is my object sigma. Yeah, so it's an easy case. In general, of course, that could have genus and all kinds of things. So now, when you meditate about what is the topology in the neighborhood on the quotient space, well, so this thing was in the Sobolev space H3 delta 0. Delta 0 only described what happened near here. You would clearly say if I change U to something which is which only modified here and is H3 closed, should be a sort of a closed object, keeping the same domain. So then, if I keep the node but change the U here and U to something which is closed in this space, then you would also consider this as a closed object. Yeah? Would make perfectly sense. So then then of course now it gets a little bit more tricky. You are going to remove the node and look at maps on this. When is that close to that object? So now, remember I described to you these gluing constructions for the gradient theory. So you can view this object here. You should think of this as, by removing the point, you think of this as a cylindrical end. And you have a cylindrical end here. So say U plus is here, U minus is here. So say U plus is restriction here, U minus there. And then you see, with a little bit of fantasy, this looks like, if I describe this here, looks like two infinite half cylinders, which of course looks very much like the two half lines which I had before. So if you make the jump from half lines to half cylinders, you define a gluing construction here. You consider objects where now you cut off part of, so you glue this cylinders together and throw the ends away. So the noded thing would be if these two things are infinitely far away, you just overlap them a little bit, so you have a long neck. So that should be a surface considered close by. And then you consider a map on it, V, and the V should be obtained by the gluing of two things which are not too far away, say of two things V and V minus, which are not too far away of the original U plus U minus. So this would be the things in the neighborhood. So I'm not going, I mean, you see already if I would write very accurate formulas and so on, it would take some time. But this gluing here is basically you cut off one, beta times V plus, and then you take another cutoff function and so on. Go from one to the other. So if the leg is sufficiently long, and you start with V plus V minus, which are sufficiently close to U plus V minus, and do this, and then now you take all equivalence classes of such object, that should be a neighborhood in the quotient space of the category. That is a neighborhood base for the topology near an object. Yeah?
In this context, the minus gluing will provide a map defined on the infinite
Yes, so the minus gluing you don't even need here. The minus gluing you only need when you want to define a chart and make it non-ambiguous. For the definition of the topology, that's good enough.
But still, so the minus gluing,
Yeah.
I mean, I would need it like to
Yes.
show that the property is present, right?
Yes. Yeah, later you need this, and the minus gluing in this case would be the following. So the minus gluing would produce. So first of all, when you look at the ends, the image. So first of all, these nodal points go to points in Q. but you have to view them as constant loops. So then the manifold itself is a manifold of constant loops. So you are actually in a Morse-Bott situation. So then where do I see the minus gluing? The minus gluing would actually be, so the minus gluing always happens with respect to something. So you have to take an original choice of curves and then describe neighboring curves by vector fields. And for the vector fields, you have a plus and a minus gluing. So the plus and minus gluing is for vector fields. The plus gluing also exists for maps. It's not apparent if you do it in Rn. You have to interpret it correctly. Then the minus gluing for vector field gives you a map, in this case, from a sphere with distinguished north pole and south pole into the tangent space at u of the node of Q, where u at the north pole is equals minus u at the south pole. That is what you would get. That would be the minus. The minus gluing would have this as the image. So the general thing, when I talked about this, so you already saw the plus and the minus gluing. I wrote some formulas, but one has to say precisely where they happen. There's a plus gluing and a minus gluing for vector fields, and there's a gluing only for maps. And they are related in certain ways. Okay, but anyway, for defining the topology, you don't need this. So you define, you pick a representative of a class in the quotient of C. And then, like this guy, and then you look at all variations of u plus, u minus. You remove the node, but leaving a very long neck, and do a gluing. And then you take the equivalence classes. This is an open neighborhood of that point in the quotient space. Then, of course, you do this around any equivalence class, and then you have to show that this has some properties. If you do it in the Gromov-Witten case for stable maps, you will find that you get a Hausdorff topology. It's not too difficult. In fact, when you work harder, you will even find it's a metrizable topology.
So what is the reason that you don't have minus gluing perhaps?
Well, I mean, it's a philosophical question rather. So I think when in Rn you can do this in general, it makes all sense. But then when you go in the manifold, you find that this only makes sense for very small tail. I mean, if you would view the minus gluing as living on the maps, you would construct things which might not necessarily exist because you don't have enough space. But if you interpret certain things like lying in a tangent space, it's like in the Rn, that makes sense. Also, the tail ends always lie in the neighborhood of a point. So why not then just assuming they essentially lie in the tangent space? I mean, okay. So now we have a topology here, and so after we settled this, we want to actually define. We want to define this local family of parametrizations. So we want to define this size. And this is when then technically all hell breaks loose, because you have to use a lot of analysis to do that, even in a sensible case. So I take this thing here. So at this point I know what the topology is, so I have already some test if my construction will be rather good. And I start here. And I want to construct neighboring objects. So obviously, some technical difficulty arises here. So I cut my problem into smaller pieces. So I would take a disk here, but I also take something which you will see why I take this. And then I take the rest, and it would be sort of overlapping here. So there will be two more localized problems. And remember, I want to say what is what is an object in the neighborhood here. And I want to solve that problem by saying what's an object in the neighborhood here and an object in the neighborhood here. And then I would put these two things together. In the case, if I know what individually the neighborhoods are, then I just say the neighborhood of a glued object. Then I would look at things here which coincide here, and are both close near to the restriction of the original object.
So one could say that you cover your domain S, comma D by open set.
What is
Care
D?
about your in your Gromov-Witten notation, right? A point in an object in C now is a tuple S, J, D.
Okay, so in general, so you have S, J, M, D, U. So then
To cover S.
yes, you would cover. So in general, so if you have even more complicated situation with genus and things here, and maybe here have a Riemann surface, then you have the action of the automorphism group, and you would choose the disks in such a way that the union of the disks would be interchanged, is invariant. So under G. So what you would get in the general case is a disjoint union of those guys, which would be interchanged by the restriction of the automorphism group action. G, you have an automorphism group G. Yes, the isotropy of this. So you would choose the disk in such a way that the disjoint union would be just invariant. Like this. So in this case, then you get sort of quite a number of those guys. And then the remaining is a possibly disconnected Riemann surface with boundary. So now, of course, in this case, in this general case, we also have to change the complex structure. But you can always arrange that you only change it away from these places where you glue. You can always take such a model. So you can actually study two problems: the disjoint union of the noded disks and the Riemann surface with boundary, where then you do the Deligne-Mumford theory there, but where the structures are constant near the boundary components. So now, let me at this point tell you that part of the black box would be this thing, which would look like.
So can you try and somehow say this a little more formally?
Yes, I will explain to you the formalism ultimately, and then it will be covered by mathematics. So you have here. So obviously here I have sort of two ends where I can glue something to. And the ends, and I view this part, this blue part, as the ends, so I would actually draw this like this. The black box, in this bubble here, something happens which I don't know, which of course means in this case telling you what the neighbor of this object is. And the blue stuff represents these zones here, and I have restriction maps. I have restriction maps onto the blue stuff by just taking an object here, restricting it to this. So now you want to have a little bit more structure. You see, the thing is, the blue stuff represents the colors. So in general, you have a little bit more structure because, you see, ultimately, abstracts, there are certain partition of unity arguments and this kind of thing. So you have to be able to talk about certain things. So let me fix something here as well, which is a little small subannulus here. And let me fix another, say suppose the Okay, so let me, yes, okay, so let me blow this up here. So let's forget this. Now comes the picture on sufficiently large, with a sufficiently large font. So, that's too large. So now, in this thing, I have an annulus here. And in this, I consider two subannuli. So that is a subannulus. This, maybe I should take the other color. And the whole thing is a blue annulus. And I have, maybe I should give some other colors here, but I don't have so many. So. Mm-hmm.
For every two domains, you're assuming that they're overlapping with the
No, it's just some. In this case, it would be annuli. Yes, for my, well, for the cases where we did it, we're annualized. But for the abstract theory, there's nothing. That is for the closed form of Witten, I get through with annuli. But the formalism will be so general, you don't even know what you're talking about when I introduce the formalism.
I'm trying to know what you're talking about.
Yes, therefore I explained to this, but it's just. So now what is the symbol for this? So
again, what are you doing? You fix, so the blue annulus is just the overlap of the two domains.
the blue one, and then there's two auxiliary annuli in there. That is, when you glue things together, you get something which you have to build a fibered product. You have two restriction maps, and they have to be identical. So what you get then, you get a subset of a product, and you have to show it's a sub-polyfold. Then you have to construct a retraction. And you basically have to don't do anything, except here you have to construct a particular retraction. And then you need the annuli. I mean, it will be taken care of by some abstract nonsense, but in concrete cases, you need particular restrictions. Yep.
So the purpose of the EP proof-like narrative, this is basically you're building your local neighborhoods by looking at these fiber products of polyfolds, just dealing with any kind of particular degeneration phenomena that can occur.
Yes. So I will have these very local constructions, and I will build fibered products which will produce this set O's.
The original O sigmas that you.
The O sigmas will be at the end fiber products of things. So now, what is the symbol for this? So this thing represents the whole object. So then, there are obviously these guys, which would represent the restrictions to this blue annuli and this blue annuli. Then there's, however, another object which we have, which is this one with a bit of green, which goes up to here. Then we have something else which we can do. We can restrict to this. Going from here, we can restrict to this, and we can restrict to this. So all these things represent spaces. So this is a whole space. This here represents taking the data here, restricting to this one. Then you can restrict to this one further. You can restrict to this one. But now what you want to do is, if you understand that piece and that piece, you want to be able to build this one. So how would you build this? Well, you just say that of this thing has a restriction to the green one, and this stuff has a restriction to the green one. This is a fibered product. You want to represent this as a fibered product associated to these pieces here.
I'm sorry, so you're describing just that one piece, or are you describing your whole node right now?
What I'm describing here is this thing here would describe a neighborhood of my. So this thing here.
We're just talking about the neighborhood of the node.
No. These pictures are describing objects in the neighborhood of my original object restricted to this one.
So let's say you covered your domain S by D1 and D2. Can we maybe mark things here?
Okay, so it's just you start with a stable curve, and I just take the restriction of my thing to this thing here.
Let's say,
Yes, so I restrict it to this.
right? So that's
So I have this thing here with a map on it.
right. That's D1.
Okay, so then this symbol describes my neighborhood construction of this object.
D1. So this is just neighborhood.
So this here is a symbol for a neighborhood of that original thing which I had here.
Just the neighborhood of the node.
A neighborhood of that curve defined on that noded surface.
So can we just give these things names?
Yes, you will.
Right? So like we used to call tau your point
Okay,
S, comma U,
You're
comma
talking about what's called U, aren't you?
Right, like U is the first picture. And
no. What I describe, so
notation.
okay, so I have this with a map. Okay, so then I take so now I build. Okay, so now I build a neighborhood of this thing. Let's call this E. E is a neighbor of this thing. It consists of all maps into Q where I remove the node and have maps on the unnoded surface, everything. The E is represented by this symbol here.
I see. So it is just the node. I mean the neighborhood of the node. It is not the entire.
No, it's just these two disks and maps on it, and perhaps also maps on the node removed.
Call this U1 because we're
No, I'm just calling it E because otherwise.
that U is not the U on the blackboard on the right.
Well, it's a restriction of the U.
Right? Can we call it something along?
Like what?
Like U restricted to D1. U restricted.
What is D1? The union of the
D1
disk.
is this neighborhood set of this domain. Okay.
So now so the black box would be a construction of a neighborhood of that object. And the black box would be represented by this picture. So now I can define, then I have a restriction of my original object to this annulus here, and can define a neighborhood of the restrictions. I have a restriction to this one, can define neighborhood of the restrictions. So what I get is, I get an E. This one,
But A is inside of E, right?
it's not inside a restrict, but so A, so let me draw a picture. So this one would be this. Then this one, A, just these lines. So what you only have are restrictions. So then here, you have an F. The F is the same thing, but with these short ends here. So maybe I put colors there then. So this is supposedly blue. Then this is green. And you have B here, and this would be the small pieces. And you have restrictions in this way. Yeah, so if I have something here, I can restrict it to these two things. If I have this here, remember this green stuff was here, I can restrict it down here. If I have this, I can restrict to the green stuff. So now, these restrictions map are SC smooth. And by construction, I constructed M polyfolds around the object. So this is a diagram between M polyfolds. And this describes the neighborhood of my first restriction to the noded disk. This describes neighborhood on the underline sound. But now, the important property you want to require is that this is a Cartesian product, which means the following.
Okay, hold on, sorry. Before we get let me get the diagram straight. So for every annulus in the overlap between D1 and D2, you draw one blue line.
Yes, that would be this large annulus.
And
And then for this,
The annulus, you draw the two little sub.
yes, so this one would be this little, so I haven't drawn this one yet. That at the moment doesn't play a role.
Your circle somehow is D1.
So this is a black box. You see, the
Hold on, let me ask you one. So the circle represents sort of the restriction to D1 minus D2.
which one, this?
Yeah.
No, what this represents is what happens sort of.
It's the complement of the annuli, right?
No, what this stands, this is a black box. The black box contains how this singularity was removed and the polyfold structure, and I don't even care what it means.
So that's what happens on the complement of the annuli, right? That's what.
That happens on the complement of the annuli, yes.
Right? And the complement of the annuli is exactly our domain D, what we've been trying to ask you to call D1, right? So D1
Yeah, but I don't know what D1 means in your case. But I know, yes, it is. Yes, so this here,
it's what happens on the complement of the other black box,
yes,
right?
yes, that would be, yes. So you have to read this symbol like something happens inside, and this is sort of rather standard piece here, where nothing happens. What happens inside is nodes are removed and maps are changed, and you have a smooth structure of this. So now, what you want to have is that this diagram is Cartesian, which means the following. So let's give them names. Phi 0, psi 0. So what you want is that the fibered product phi 0 psi 0a is a sub-polyfold of the product F cross A. The first thing. So what does that mean here? These are the things who have the same restriction on. So what is F cross A? F of A is any map here times any map here.
Could you box the things and call them?
Okay, F.
Yeah, can you box
So this is F.
Okay.
This here is B, and this is A. An element in the product of F and A is something here, the map here, and a map here. If you're in the fibered product, it just means the restriction to this thing is the same, which should be precisely that element, an element here. But the fiber, the first requirement, the fiber product is a subpolyfold of this, and the next thing is this map psi phi is a diffeo, which means that anything here can be explained as a fibered product of something here with that, where the relationship is the coincidence of that restriction. So you can do the same with bundles, and you can talk about sections of this. You can incorporate everything you want. So why do I need this blue stuff? Well, I need the blue stuff because I want to connect it with other stuff I constructed. Yes, you can. Yes, what this says is you construct F independently and A independently, and then you look that the restrictions coincide, and then you take the smooth structure induced from the product, and that's essentially the structure which you have on E. I mean, in principle, you are interested in the E, but in order to say how you connect E with another E prime you construct, you need some restriction. So now, let's assume now, by keeping the thing simple, I have just one exit. So then, that means whatever happens here, I don't care. So I would have some, so this thing would be blue here. Oh, thank you. So blue is on the here's more blue even. Okay, so I have this blue, and I have the green here, and then of course have the blue. And then I would have this other object here with this little bit of blue. And taking this object together with this object by restricting to this one, I can reconstruct this. So why is that good? The thing is, quite often you can make local constructions here and extend them by the identity, and then you get a global construction of the origin space, for example. Yeah? So for example, if you make a construction here on the blue stuff, which does not change the restriction to the green stuff, it can always be extended by the identity to the full thing. So it allows you a fantastic amount of, if you give a little bit of local information, you can make global constructions out of this. Okay, so suppose this is one thing, and suppose we would have another black box here, and I want to put them together. Then obviously, what I have to require is that I have the same set on which I can restrict to. So now this one would come with something red here. So then I would have, so let's color this here, white. So it's another black box, and then I would have something here, and I would have maybe a smaller, but here this would be red. And I would have this. So now what I want to do is,
Sorry, so E, A, B, and F now all represent polyfolds?
yes, they're all polyfolds. It's a particular diagram of polyfolds. So the thing is, what does it mean on an abstract level that the restrictions of two maps on some subdomain are the same? It's just the only language, if you want to say not too much, is just a fiber product. For restrictions are the same.
So eventually you want this, you want for each of the symbols, you want not just a polyfold, an M polyfold, but also a bundle and
You bundle and a section.
a section.
Yes. And then
So now,
a
how do you, so somehow you're assuming some sort of locality of your section, right?
some kind of semi-locality. I mean, you want to make that certain sections make sense. And then if you have bundles, they would all come with sections, and there would be certain compatibility with the sections and these maps which you have. So now if I have another black box, of course the requirement is I want to build the fibered product of these two black boxes by restricting both to the blue line. And then I want, yeah, so if I have two black boxes which both restrict to the same thing, you want to build a fibered product. Now, these two guys both restrict to the blue line, you want to build a fibered product. The only thing what you can't say without additional structure is that this fibered product is actually a subpolyfold of the product. So you need a property for that. And it turns out that this property can be formalized in a quite easy way which guarantees this. Yeah. So let's make a break here, and then so everybody can recover mentally, and then we continue.